Hello students, welcome to IMS GATE Academy. Today I am here to discuss about the index properties. Now my dear students, why do you want to study about the index properties? Remember students, if you want to study the soil classification, how do you want to classify a soil? Index properties will help you. And also, if you want to understand the engineering properties of the soil, index properties will help you. So index properties is a property of the soil, is the properties of the soil where it helps you to classify the soil and also to understand the engineering properties of the soil and also to understand the engineering properties of the soil. Now see students, let us go into the topic index properties. Let us go into the topic index properties. Now when I talk about the index properties, as I told you, index properties are useful for what, my dear students? Index properties we study, these will be helpful, or you can say index properties are useful for the classification. Index properties are useful for classifying and identifying the soil. Index properties are useful for classify and identify the soil. To classify and identify the soil, we study about the index properties. And remember, my dear students, index properties also provides information or rough estimation of information about the engineering properties of soil. What are engineering properties of soil? Permeability, how the water will flow in the soil, that is nothing but permeability. Shear strength and compressibility. So these are some of the engineering properties. So if you want to have an idea about the engineering properties, you should also study about the index properties. Now actually, my dear students, based on the soil classification, lot of information can be gathered about the soil nature and the properties. So that is the reason we study about the index properties. Now see students, when I talk about the index properties, if you see in the soil, broadly soil can be discussed about two parts. Broadly we discuss the soil into two parts, or we classify the soil into two parts. What are the two parts when we broadly classify are? The one is the coarse grained, and other one we have is the fine grained soils. So when I talk about the soil, we talk either about coarse grained or we talk about the fine grained soil. So my dear students, when I talk about the coarse grained or fine grained soils, actually which will help for the classification of coarse grained? See students, remember sieve analysis and relative density. Okay, my dear students, sieve analysis and relative density will be helpful to classify the coarse grained soil. To classify the coarse grained soils, my dear students, people try to read about the properties like sieve analysis or relative density. Similarly, my dear students, if you want to have an idea about the fine grained soils, like we have the limits like consistency limits, and also we should have an idea about the sedimentation analysis. So broadly soils are classified into two parts, my dear students. One is the coarse grain, another one is the fine grain. So what actually the properties will help you to classify the coarse grain? So when I talk about sieve analysis and relative density, these are the properties which help you for the classification of the coarse grain. Similarly, my dear students, when you talk about the consistency limits, where you can expect a problem. My dear students, in GATE 24, when I am discussing about the consistency limits, please be attentive and be focused. And coming to the sedimentation analysis, based on the settling velocity, the soils are classified. So we'll discuss these parts in a broader picture when it comes to the individual terms. Okay, so you are going to say that through the index properties, you are going to classify the soil. So let us understand one important graph, that is nothing but the particle size distribution curve. See, my dear students, in most of my lectures also, I have been telling this. Okay, what do you mean by particle size distribution curve? What I have been telling in the most of my lectures? Sir, when you draw a graph, what you will be denoting on the x-axis and what you will be denoting on the y-axis. When you denote something in x-axis, it is nothing but the independent quantity and the dependent quantity on the y-axis. So let us understand the particle size distribution curve. So actually here comes the particle size distribution curve. So on what basis you are going to draw this particle size distribution curve? So through particle size distribution curve, what is the outcome of this graph? So these things first let us understand. It is a graph drawn between the percentage finer. It is a graph drawn between the percentage finer and the particle size dia. Based on the percentage finer and the particle size, a graph is drawn. So let us see how this graph will look like. Here is the graph. Now see students, the first we have seen, suppose I will assume this as a graph A, and I will assume this graph as B, and I will assume this graph as C. Okay. Now what does the graph A suggest to you? The graph A suggests that it is a well-graded soil. And what is the graph B tells you is, it represents a poorly graded, or gap graded soil. Agree students? Is it poorly graded or gap graded? No. I have written intentionally, B is not the poorly graded or gap graded. You have to see here students. See, one second. This C graph is a poorly graded or gap graded soils. Why I have written, I will tell you. And this graph will represent uniformly graded. So as an engineering student, you should understand from the graph some results. Sir, actually based on the shape of the graph and also based on the activity of the graph, you should understand some summary. So if you see the graph here, this graph, all the particle sizes are present in this graph. If you see this graph, all the particle sizes are present. So well-graded soil definition is, it is a soil where particles of all sizes are present. When do you say that a soil is well-graded? When the particles of all sizes are present, then it is called a well-graded soil. And when do you say that a soil is uniformly graded? If you see here students, in uniformly graded, if you draw a particle size, all the particles are of same size. When all the particles are of same size, my dear students, we call that soil as uniformly graded. If you see here this graph, see this is poorly or gap graded because some particle sizes are missing. So let us conclude this student, just go through the graph. Okay students, so what is a well-graded soil? A well-graded soil is a soil where particles of all sizes are present. So what is the shape of well-graded soil from the graph is, it is S shape. When I talk about poorly graded, how is the shape student? The shape is nothing but the hump shape. When you see the uniformly graded, where the particles are all are of same size, then it is indicates a steep slope. So remember, my dear students, through the particle size distribution curve, you are going to understand whether the soil is well graded, or whether the soil is uniformly graded, or whether the soil is poorly graded. So from this graph, it is evident whether a soil is uniformly or well graded or poorly graded. So let us understand there are two coefficients, my dear students. There are two coefficients. One is the coefficient of curvature, okay, and other one we have is the coefficient of uniformity. Now, my dear student, what is actually a coefficient? If you tell coefficient of friction, what do you mean by coefficient of friction? Based on the coefficient of friction, what you are going to understand? See student, based on the coefficient of friction, you are going to understand the surface, whether it is rough or smooth. Similarly, what is the purpose of learning coefficient of curvature? What is the purpose? Curvature, the name itself. So, the coefficient of curvature represents the shape of the curve. So, to understand the shape of the curve in a particle size distribution, the coefficient of curvature will help you. To understand the shape of the curve, you are going to study about the concept called coefficient of curvature. Now, my dear students, coefficient of curvature is given by the formula d square 30 upon d60 into d10. And definitely now you will ask me, sir, what is this d30, d60 and d10? Definitely you will ask me. Remember, my dear students, people will have a lot of queries regarding this. First of all, whether it is d30, d60 or d10, first of all, understand that it is a sieve size. d30 is nothing but the sieve size where 30% of the soil particles are passing. If I talk about d60, it is the size of the sieve where 60% of the soil particles are passing. If I talk about d10, it represents the size of sieve where 10% is passing. So here 60, 30, 10 represents the percentage of passing. So my dear students, when I talk about d10, this is called as effective size. My dear students, only d10 is called as the effective size. They can ask you which is considered as effective size means d10, or they can give you d30, d60 and the coefficient of curvature, and they will ask you to find out the effective size. Okay. So when I talk about the effective size, thank you Vasukiran. So when you talk about the effective size, d10 is the size of the sieve. So here, my dear students, the effective size can be expressed in mm. Okay, the effective size can be expressed in mm. Why? Because it is nothing but the size of the sieve. So let us understand how this coefficient of curvature will help you. Suppose, my dear students, if the coefficient of curvature value lies between 1 and 3, it represents a well-graded soil. When you have calculated the value of coefficient of curvature and you have received a value, or you have got a value between 1 and 3, definitely that value will help you to understand whether it is a well-graded or poorly graded or uniformly graded. And remember, my dear students, coefficient of curvature is approximately equal to 1 in case of uniformly graded. So let us conclude this coefficient of curvature, my dear students. Let us conclude this. Why do you want to study about the coefficient of curvature? Because to understand the shape of the particle size distribution curve, we study about the coefficient of curvature. Similarly, the coefficient of curvature is given by the formula d square 30 upon d60 into d10, where d10 represents the effective size. Similarly, my dear students, we have a concept called coefficient of uniformity. Now, why do you want to study about the coefficient of uniformity? You told me that, students, coefficient of curvature is helping you to find out the shape of the curve. Now, where you want to learn? Why do you want to learn the coefficient of uniformity? Remember, my dear students, the coefficient of uniformity represents the particle size range. Okay, it gives you idea about the particle size range. Means whether the soil particles are ranging from 0.2 micron to 200 mm or 4.75 mm. So it gives you idea about the particle size range. Means if you take a soil sample, what is the minimum size of the soil and what is the maximum size of the soil. So you can understand the range of the soil particle size by understanding the coefficient of uniformity. And coefficient of uniformity is given by the formula Cu is equal to D60 upon D10. Okay, Cu is represented by what? D60 upon D10, where D10 represents the effective size. As I told you, D60 represents the size of the sieve where 60% is passing. Now see, students, when the value of Cu greater than 4, if the value of Cu is greater than 4, then we call it as well-graded gravel. If Cu, coefficient of uniformity, is greater than 4, we call that soil as well-graded gravel. And if the value of coefficient of uniformity is greater than 6, we call it as well-graded sand. And for uniformly graded soil, Cu will lies between 1 to 2. When the coefficient of uniformity value lies between 1 to 2, then we take that soil as uniformly graded. So, my dear students, you study about the coefficient of uniformity to get an idea about the particle size range, and we have a coefficient of uniformity formula D60 upon D10, where Cu greater than 4 represents well-graded gravel, Cu greater than 6 represents well-graded sand. When the value of coefficient of uniformity is between 1 and 2, then it is represented as uniformly graded soil. I hope this is clear for you. So, my dear students, actually we will be studying about the plasticity chart and all, but for your remembrance purpose and for problem solving, I am telling you, for any soil to be well graded, it should satisfy both the conditions of Cu and Cc. If any one of the condition is not satisfied, then we treat that soil as poorly graded. Just write it as a note, my dear students. I repeat the point again. For a soil to be well graded, the coefficient of uniformity and the coefficient of curvature the coefficient of uniformity and the coefficient of curvature, both coefficients value to be satisfied. If any one condition is not satisfied, then we treat it as poorly graded soil. Now let us go to the important part, that is the sieve analysis. Okay. So what is actually a sieve analysis? See, students, if you talk about the sieve analysis, we have different sizes like 4.75 mm, 2.36 mm, so on up to 2 micron. Okay, so what is this 4.75 mm or 2.36 or 2 micron will represent is, this represents the sieve size. What does this represents? This represents the sieve size. And from this sieve size, you will find out how much weight is retained on each sieve. So let us assume you have collected a soil of weight total W, and the sieve retained on each, and the weight means the weight of the soil retained on each sieve is W1, W2, so on up to Wn. Now, my dear students, you have to calculate the percentage weight retained. You have to calculate the percentage weight retained. And how do you calculate the percentage weight retained? The weight retained on each sieve multiplied by 100 upon the total weight. Okay, similarly we can write W2 upon total weight W into 100, and if you take for N soil, Wn by W into 100. So my dear students, the percentage weight retained on each sieve, let us assume it as x1, x2 and xn. Here we have to calculate the cumulative weight retained. Here you have to calculate the cumulative weight retained. Now when I talk about the cumulative weight retained, it is nothing but the sum of the weight retains. So cumulative weight retained is given by the formula, x1, x2, so on, xn. When I talk about percentage finer, here see students, when I talk about the percentage finer or percentage passing, you can write it as 100 minus x1, 100 minus of x1 plus x2, and here you can write it as 100 minus of x1 plus x2, so on up to xn. So this is how actually, my dear students, if you don't have an idea about the sieve analysis, you cannot find out the effective size or D60 or D30 or anything. Suppose see student, you have observed at 2.36 mm, the percentage finer is 60, or the percentage finer is also called as percentage of passing. At this sieve size, if there is a 60% passing, then we consider this sieve itself as D60. So my dear students, the practical and the most usable way to classify the soil is nothing but the sieve analysis. Using the sieve of different sieves, like we have a set of standard sieves which are having 2.75, 4.75, 2.36, and you will be doing the sieve analysis. Based on how much amount of the weight of soil retained on each sieve, you are able to classify the soil. I hope you are clear with this sieve analysis concept. And when you are solving previous gate questions, how to find out percentage without finding the percentage of passing, you cannot find out D10, D60 or D30. This kind of question was observed in one of the gate question, my dear students. Now let us talk about the concept called relative density. Let us talk about a concept called relative density. Now see students, what do you mean by relative density? Why do you want to study about relative density? As I told you, relative density is also useful for the classification of coarse grain. Here relative density is also known as density index. So my dear students, when you see the formula relative density, they will show it as ID. So even when I am studying my BTech, preparing for GATE exam, why relative density is denoted as ID, I used to have this doubt. Because the alternate name, the other name of relative density is density index, that is the reason it is denoted by ID. So here relative density ID is given by the formula E max minus E upon E max minus E minimum into 100. So here my dear students, density index is given by the formula E max minus E upon E max minus E minimum. So what is E max here? What is E max is, when will be the void ratio will be maximum, my dear students? You have to use the common sense. The void ratio will be maximum in case of loosely deposited soils. So E max represents the void ratio, or you can say void ratio in the loosest state. So here my dear students, based on the maximum or minimum, the state of the soil can be understood. So here E max represents the void ratio in loosest state. Okay. Now my dear students, when I talk about E minimum, what do you mean by E minimum? E minimum is nothing but the minimum void ratio. So the void ratio will be minimum in case of what, my dear students? In case of dense state, the void ratio will be minimum. In case of dense state, the void ratio will be minimum. Then what does E represents? E represents the void ratio in natural state. Void ratio in natural state. Now immediately, my dear students, sir, you are telling that relative density is helpful for the classification of coarse grain. Is there any purpose to study relative density? Yes. Relative density will give you the idea about the relative compaction. My dear students, what do you mean by relative compaction? You will be studying in compaction. Relative compaction is nothing but the dry density in the field by maximum dry density in the laboratory into 100. Through relative compaction, how the soil layers can be compacted relatively, you will get an idea. So relative density is also known as density index. Using the formula E max minus E by E max minus E minimum, it represents the void ratio is maximum in loose state and the void ratio is minimum in the dense state, and void ratio represents in natural state is nothing but the value of E. Here through relative density, you will get an idea about the relative compaction. What actually is relative compaction? How the soils are compacted, or it is defined as the ratio of dry density in the field upon maximum dry density obtained in the laboratory multiplied by 100. Now see students, based on the relative density, we can also classify a table. If suppose the relative density value is 0 to 15 percentile, the state of the soil is very loose. If the density index is 0 to 15 percentile, the state of the soil is what? It is very loose soil. Suppose, my dear students, if the density index is 15 to 35 percentile, the state of the soil is loose. If the relative density is 35 to 65 percentile, it is known as low dense. And if the value is 65 to 85%, we take it as dense, or you call it as medium dense. Or if the value of density index is more than 85%, you will classify the soil as highly dense. So based on the density index, we can identify the densification of the soil. The relative compaction is nothing but to have an idea about the how we can densify the soil by applying the compaction. So using the relative density, you will get an idea how to classify the coarse grained soil. So let us go into the most important part, and we have the term called consistency limits. We have a term called consistency limits, or we also call it as consistency limits, or also called as Atterberg limits. What is consistency limits, are also called as what? Consistency limits are also called as Atterberg limits. We have called consistency limits or Atterberg limits. Actually, these consistency limits or Atterberg limits will help you to solve the problem to identify the fine-grained soils. So here, my dear students, when I talk about the fine-grained soils, here you should understand how do they define fine-grained soils. How do they define the fine-grained soils? One second, students. Okay. Okay. Now see students, before understanding the consistency limits, we should have an idea of this graph. Okay. Let us draw this graph. Now see students, suppose we will understand from this graph what are consistency limits. Let me draw this diagram, students, then you will get an idea. Suppose we have here shrinkage limit. Here we have the plastic limit, we call it as. and here we have the liquid limit. Here we call it as solid state. Here we write it as semi-solid state. And here we write it as plastic state. And here we write the liquid state. Okay. Here comes the liquid state. Okay, now see students, for your information, what is WS, WP and WL? WL, WP, WS are nothing but the consistency limits or Atterberg limits. So what are consistency limits or Atterberg limits is, this is nothing but the liquid limit, plastic limit or shrinkage limit. So what actually is consistency limits or Atterberg limits? Let us study. These are the water contents. So first of all, it is a graph drawn between volume and water content. It is a graph drawn between volume and water content. Okay, we denote this as VD, that is volume at dry state. We will discuss more in detail in the later of the slides. So what are consistency limits or Atterberg limits? These are nothing but the liquid limit, plastic limit and shrinkage limit. So here from the graph, you should understand these are the water contents at which soil passes from one state to the other state. So what are Atterberg limits or consistency limits means? These are the water contents. These are the water contents at which, these are the water contents at which soil passes from, one state to the other. These are the water content at which soil passes from one state to other state. Okay, I hope you are clear with the Atterberg limits or consistency limits. First of all, from the graph, these are the water contents at which soil passes from solid to liquid or semi-solid to plastic or plastic to liquid state. Here, my dear students, from the graph, it is evident that liquid limit is greater than, plastic limit greater than, shrinkage limit. Yes or no? Why? Because this was one of the IES questions, student. If you represent the numbers in a graph, you represent 1, 2, 3. So obviously when you move towards the right side, definitely that values will be higher. So if they ask you what is the order of the Atterberg limits or consistency limits, liquid limit is greater than the plastic limit and plastic limit is greater than the shrinkage limit. So what are Atterberg limits? You are clear. So let us discuss the concept called liquid limit. Let us understand what is a liquid limit. My dear students, what do you mean by liquid actually? A liquid is nothing but having no shear resistance. So what is a liquid limit is, it is the minimum water content at which, so here I would like to tell you, you please understand what is a liquid state. It does not have any shear resistance. But what do you mean by liquid limit is, it is the minimum water content at which soil has small shear resistance. At liquid limit, you should understand the soil will have small shear resistance. Means when you cross the liquid limit, the shear resistance will be almost zero. So it will have a small shear resistance against the flow. That water content can be considered as a liquid limit. And another important term I would like to tell you, liquid limit is determined by an apparatus called Cascades apparatus. Liquid limit is determined by an apparatus called Cascades apparatus. So see students, here if you see in a cascaded apparatus, what they will do is, they will take a soil with a groove. Okay, a soil is cut by a groove. of standard dimensions, when you apply 25 number of blows, when you apply the 25 number of blows, add the 25 number of blows, you will understand that the soil is moving for a distance of 12 mm. That will be considered as, that water content will also be considered as liquid limit. So, shall I explain you the theoretical part? It is the minimum water content at which the soil has small shear resistance. When I talk about the practical part, a soil is cut by a groove. There is some standard dimensions for that. On impact of 25 number of blows, the soil will move a tendency of 12 mm under an impact of 25 number of blows. Whatever the minimum content which the soil has to move for a distance of 12 mm, that will also be considered as liquid limit. So, my dear students, if you talk about the graph, if I have drawn a graph between water content and, if I have drawn a graph between number of blows, okay, and water content, if you see here at 25 number of blows, you will get the liquid limit. Yes or no? At 25 number of blows, you will get the liquid limit. So, this is from the graph. And one more thing, my dear students, they can ask you, here usually they use the base as rubber. If the base is softer than rubber, then definitely the number of blows will increase. Good afternoon, Atul. Good afternoon. If the number of blows, see here, if the base is rubber, if the base is softer than rubber, the number of blows will increase and definitely the liquid limit will also increase. So, this is the definition of liquid limit. Now, my dear students, we have a curve called flow curve. Sir, if you understand this flow curve concept, actually I used to ask most of my students in the offline classes also, sir, what is a flow curve? Why do you want to draw the flow curve? Flow curve gives you an idea about the shear strength. To give an idea about the shear strength, we study about, it gives you an idea, means rough idea about the shear strength of the soil. Okay, it gives you idea about the shear strength of the soil. Now, my dear students, how do you find out the flow index? Okay, now see students, if I have drawn a graph between the water content, as I told you, and number of blows, if I draw the graph between water content and number of blows, initially the graph seems to be like this. So, at different water content, at different number of blows, see student, higher the water content, lesser the number of blows. More the water content, higher the water content, lesser the number of blows. Lesser the water content, higher the number of blows. So, my dear students, I have a question for you. What is a flow curve? It is a flow curve gives you idea about the shear strength. It is a graph drawn between water content and the number of blows. So, here the graph represents a curve. Now, I want to make it a straight line. To make it a straight line, what we have to do? See students, this is a very simple and concept. If you apply the logarithm to the x-axis to log to the number of blows, then definitely this will become a straight line. Why? See students, if you see the log 1 variation is 0 and the log 100 variation is 2. Most of the people should understand also in fluid mechanics, HHM lab, wherever you see in graphs, they try to apply the logarithm. The reason is how this curve will become a straight line. That is a simple basic thing. Why? Because for this much variation, the y variation is very small. If you see the x variation, it is 1, it is 0. And if you see the x variation is 100, the variation is 2. Log 10 square, you can write it as 2. So, when the x variation is from 0 to 100, the y variation is very small. So, that is the reason actually when you apply a logarithm, this can be converted into a graph, and if you plot the graphs, the values will be very close to the straight line. So, that's how it came. Or you can write from the differential equations, you can derive it from a straight line equation. So this is the common example how the curve can be made into a straight line. That is the reason when you talk about the coefficients or anything, they try to understand that a logarithmic effect or finding the coefficients using logarithmic formula or square root fitting method or a square curve fitting method and all. These are the different concepts. So here flow curve gives you idea about the shear strength. Now see student, the slope of the flow curve, suppose if I have taken water content, it is a decreasing graph because higher the water content, lesser the number of blows. Lesser the water content, higher the number of blows. So it's a decreasing graph. So I take higher value here and W1, W2 and here we take N1 and N2. Now remember my dear students, the slope of flow curve, the slope of flow curve, the slope of flow curve is what? The slope of the flow curve is nothing but the flow index. And this flow index is represented by what, students? It is represented by IF. And IF can be written as W1 minus W2 upon log N2 by N1. Because log A minus B can be written as log A by B. So here what is slope? Y2 dy by dx, y2 minus y1 by x2 minus x1. y2 minus y1 is w1 minus w2. x2 minus x1 is log n2 minus log n1. Log a minus log b can be written as log a upon log b. So my dear students, the slope of flow curve is nothing but flow index and it is given by the formula w1 minus w2 into log of n2 by n1. Log of n2 by N1, where N1 represents the number of blows and N2 also represents the number of blows. So this might be helpful to understand, to get an idea about the shear strength. And one more thing, students, whenever you are performing this test, soil passing through 425 micron is used in this test. So this how we talk about the flow curve. So let us discuss about the term called plastic limit. So let us discuss about a term called plastic limit. And a plastic limit is represented by what? It is represented by WP. So what is actually a plastic limit? My dear students, when you add some water into the soil, you can make the soil into a rope. Okay. Now when you make that soil into a rope of diameter 3 mm, the rope should not break. So that is the reason plastic limit is determined by the practical test, thread test, or it is the minimum water content at which a soil can be rolled into 3 mm diameter without breaking or crumbling, and we call this test as thread test. So what is this? As the minimum water content, the minimum water content at which soil can be rolled into 3 mm diameter, at which a soil can be rolled into 3 mm diameter is known as plastic limit, and the test is known as thread test. Okay. So here my dear students, you should apply this practical test to identify the plastic limit. Okay. Next, similarly, we talk about the next term is very important, that is known as shrinkage limit. Here comes the very important concept. Okay. What actually is shrinkage limit? And this question can be expected in GATE question number. In 24, we can expect a question from this consistency limits. So please be careful while you are solving, while you are understanding this shrinkage limit. So what is shrinkage limit? It is represented by WS. Shrinkage limit is represented by what? WS. Or it is the minimum water content. Shrinkage limit is nothing but the minimum water content. It is the minimum water content. Shrinkage limit is the minimum water content at which the soil is It is the minimum water content at which the soil is fully saturated. It is the minimum water content at which the soil is fully saturated. Now, my dear students, if I talk about the void ratio, water content and specific gravity, here you might be knowing E is equal to what? Water content to G upon SR. Here void ratio E is given by the formula E is equal to water content to G by SR. So here what he is trying to tell you is the water content will be minimum at degree when the degree of saturation is when the degree of saturation is fully saturated, means SR is equal to 1. So from this formula we can write shrinkage limit WS is equal to E upon G. Okay. So here shrinkage limit can be written as what, my dear students? Shrinkage limit is written by the formula E upon G. Actually, my dear students, you should also understand the important term, like there is another term also. How do you define the shrinkage limit? There is also another important term. How do you define the shrinkage limit? Okay. So for that, I just want to show you the same graph which I have drawn, Amma. Okay, so here you know this is 1 second. Here we write it as what? Shrinkage limit. This is plastic limit, and this is liquid limit. Okay. Now you know what is the state of the soil. Here it is semi-solid, solid, semi-solid, plastic and liquid state. Sir, see the graph which I have drawn earlier. If you see the graph which I have drawn for the consistency limits, this is solid state, semi-solid, plastic, and there we have represented it as shrinkage limit, plastic limit and liquid limit. So here the same case, what I would like to tell you here is, what is a shrinkage limit? You told that it is the minimum water content at which the soil is fully saturated. But remember one thing, students, here the volume is represented as VD. The practical definition is what? It is the minimum water content at which the soil is fully saturated. But if you see up to shrinkage limit, the volume is constant. You can write the shrinkage limit definition as it is the maximum water content up to which the volume remains constant, or it is the maximum water content, any further loss of moisture does not cause any change in volume. Are you getting me? So here you have written shrinkage limit. There might be loss of moisture and the water content might reduce, but there won't be any change in the volume. That water content can also be taken as the shrinkage limit. So shrinkage limit is the minimum water content at which the soil is fully saturated, or it is the maximum water content up to which any further loss of moisture does not cause any change in volume, is known as the shrinkage limit. I hope you are clear with the shrinkage limit. So let us see, actually there is a concept called shrinkage ratio. Now my dear students, shrinkage ratio is defined as the, see students, this is very important. It is defined as the volume change. Shrinkage ratio is defined as the volume change, whatever there is a change in the volume, expressed in terms of dry volume change expressed in terms of dry volume to the corresponding change in water content. What, sir? Shrinkage ratio is defined as the volume change expressed in terms of dry volume to the corresponding change in water content, to the corresponding change in water content. So here, my dear students, okay, so what is actually this shrinkage ratio? See students, suppose if I have considered the volume at plastic limit as Vp, and if I consider the volume at liquid limit as VL, so shrinkage ratio is defined as the change in volume. So if you write change in volume is VL minus Vp, and this should be expressed always in terms of dry volume. So VL minus Vp upon WL minus Wp, or you can write it as Vp minus Vd, because this is also a volume change, but here you should take that volume as Vd upon the corresponding change in water content is Wp minus Ws, or you can write it as VL minus Vd upon Vd upon WL minus Ws. So all these, because the slope will be same, you can write here the shrinkage ratio is terms defined as the, it is defined, what is this? This part will represents the, this will represents the volume change. This represents the volume change in terms of dry volume, which is Vd, upon the corresponding change in water contents. So what is shrinkage ratio? It is the volume change expressed in terms of dry volume to the corresponding change in water contents is nothing but shrinkage ratio. And remember, my dear students, shrinkage ratio, we can write shrinkage ratio also as it is the mass specific gravity in dry state. Another important, my dear student, because there is no change in the volume, Vd, dry volume, it is also defined as the gamma D by gamma W, shrinkage ratio, which is a very, very important formula to solve the problems. So remember, please write this as a note or an important point. Shrinkage ratio is defined as the mass specific gravity at dry state. So my dear students, when I talk about the shrinkage limit is given by the formula E upon G, where E represents the void ratio and G represents the specific gravity. Similarly, the shrinkage limit can also be written as 1 by Gm minus 1 by G, 1 by G minus 1 by G. And similarly, some students might be asking me, sir, it is difficult to remember these formulas. If I write G minus Gm, then what it will happen? It will be negative, sir. Every time G, because G is always greater than Gm, then 1 by Gm will be more than G. That is the reason how I remembered. Or usually simply you can write shrinkage ratio is nothing but the volume change expressed in terms of dry volume to the corresponding change in water contents. So I hope you are clear with these two important formulas. Similarly, my dear students, there is a laboratory test to determine the shrinkage limit. I will be discussing in the problematic part. Now, my dear students, if I talk about the volumetric shrinkage, if I talk about the volumetric shrinkage, if I talk about the volumetric shrinkage, what do you mean by volumetric shrinkage? Volumetric shrinkage is nothing but the, if I talk about the shrinkage ratio, you told it is the change in volume to in terms of dry volume to the corresponding change in water contents. So when I talk about the volumetric shrinkage, so let us move on to the next slide. If I talk about the volumetric shrinkage, sir, shrinkage is nothing but what? Volume reduction. Actually, if you take a cotton cloth and if you immerse it in a water, what will happen to that cotton cloth? It shrinks. So due to that, there is a change in the volume. So when I talk about the volumetric shrinkage, so it is nothing but the change in volume in terms of dry volume. Whatever the change in volume in terms of dry volume. Suppose this can also be written as shrinkage ratio into liquid limit minus Ws. So for your information, there can be different formulas. But now you have to understand the static formula, what actually is the volumetric shrinkage. So students, if you want to understand whether the soil is bulging or swelling, these will also help you or to classify the soil. Volumetric shrinkage is defined as the volume change, volumetric shrinkage is defined as the volume change expressed in terms of dry volume. The volumetric change is defined as the volume change expressed in terms of dry volume is nothing but the volumetric shrinkage. So we can have different formulas while you are talking about the volumetric shrinkage. So here now let us see the important part, and remember liquid limit is always greater than, plastic limit is always greater than the shrinkage limit. So these we call it as Atterberg limits, and here we have an important formula. Shrinkage ratio is defined as 1 by GM, shrinkage ratio is defined as GM, that is equal to gamma D upon gamma W. And there is another formula for shrinkage limit, WS is equal to E by G, or that is equal to 1 by GM minus 1 by G. And remember, my dear students, there might be some problems in GATE exam where you should be aware of the graph. If you are not aware of this graph which I have shown you, then it will be very difficult to understand the problem. So please keep it as a note. You have to be aware of the graphs when you are solving these problems. Now let us discuss some of the important indices. So we have another thing. We also have to talk about some of the important indices. We also have to talk about some of the important indices. Okay. When I talk about some of the important indices, the first and the foremost important index is the plasticity index. The one of the first and the most important is what, sir? Plasticity index. And using this plasticity index, measure of the soil is classified. So plasticity index IP is given by the formula, you can write it as WL minus WP. So plasticity index is given by the formula what? It is given by the formula liquid limit minus plastic limit. So based on the if suppose IP value will be taken, if it is negative, we take it as 0. When the IP value is 0, the state of the soil is, we take it as non-plastic. 0 or negative, we take it as non-plastic state. What is plasticity means? It is the property of the soil which allows to deform but without any rupture. If you talk about consistency, it is the property of the soil which offers resistance against the deformation. In plasticity, it is allowed to deform but without rupture. If the plasticity index is less than 7, we take that soil as low plastic. If the plasticity index is between 7 to 17, we take that soil as medium plastic. And remember, if the plasticity index is more than 17, we take it as highly plastic. So here, my dear students, when I talk about the plasticity index, the state of the soil and all, we have different types of soils. When it is 0, non-plastic, when less than 7, it is low plastic, and 7 to 17, medium plastic, and more than 17, it is highly plastic. So let us see what are the important indices. The important indices are nothing but the one is plasticity index, which is defined as the liquid limit minus plastic limit. Next we have is the shrinkage index. Okay, through shrinkage index also you are going to all these indices will help you to understand all these things will help you to how to classify the soil. Here shrinkage index is denoted by IS and it is given as WP minus WS. Okay, shrinkage index based how, if you talk about swelling or shrinkage limit, swelling or shrinkage, you will get at least an idea. And also, my dear students, we also have a factor called toughness index, means how the soil will offer resistance against the deformation. For that, you have to understand what is the toughness index. And toughness index is given by the formula IT. It is equal to plasticity index upon flow index. The slope of flow curve is nothing but the flow index. So I hope you are clear with the indices. One is the plasticity index, liquid limit minus plastic limit, and here shrinkage limit, plastic limit minus shrinkage limit, and we have the toughness index, that is plasticity index upon flow index. Similarly, we have another important term called consistency index. As I told you, what is consistency? It is the property of the soil which offers resistance against the deformation. So how do you, what is the formula for consistency index is, see students, IC, consistency index is given by the formula IC. IC is equal to what? You can write it as WL minus W upon IP. When I write IC is equal to WL minus W upon IP, then we write it as the consistency index. And remember, my dear students, what will be the value of consistency index? At liquid limit, the value of the consistency index will be 0. At liquid limit, the value of consistency index will be 0. And at plastic limit, the value of consistency index will be equal to 1. At plastic limit, the value of consistency index is 1. And at shrinkage limit, the consistency index will be greater than 1. So based on the different states of the soil, the value of the consistency index will be identified. So another important term I would like to discuss is the liquidity index. And remember, my dear students, liquidity index is given by the formula IL. How do you represent liquidity index? Liquidity index is represented by a formula called IL, and IL is represented as W minus WP upon IP. Now, my dear students, I will tell you the shortcut how I remember. If you see in consistency index, there is a C, so L will be there. But if you see liquidity index, L won't be there. Just for your remembering, I am telling you. Because see, using the liquidity index, now see student, suppose at liquid limit, the liquidity index will be equal to how much, sir? 1. Now, at plastic limit, the liquidity index will be equal to what, sir? It will be equal to 0. And at shrinkage limit, the liquidity index will be negative. So here I would like to tell you one important thing. So here you observe what are the values of consistency: 0, 1, 1 greater than 1. And here if you see 1, 0, minus 1. Okay, not minus 1, you can write. You should not write minus 1. It should be less than 0. Or because it is a negative value. That's what I would like to. W, because shrinkage limit is less than plastic limit. Now see students, why this happens, I will tell you. You have written the formula IC plus IL. Okay, based on this you can also understand. What is IC? IC is represented as WL minus W upon IP. Okay, what is liquidity index is W minus WP upon IP. If you solve this equation, the LCM will be equal to plasticity index, that is IP. You can write it as WL minus W plus W minus WP. And if you have cancelled this minus W, this will be equal to 1. So here, my dear students, I would like to tell you the value of the consistency index plus liquid limit plus liquidity index can be written as 1 or 100 percentile. It can be written as what, sir? It can be written as 1 or 100 percentile. I hope you are clear with the consistency index. So let us see, we have another important term called activity ratio. We have an important term called activity ratio. Now, my dear students, activity ratio is defined as the ratio of plasticity index to the percentage of clay fraction. How do you define activity ratio? Activity ratio is defined as the ratio of plasticity index to the percentage of clay fraction. When I talk about it is defined as the ratio of plasticity index to the percentage of clay fraction, why do you want to study about the activity ratio? See students, the swelling and shrinkage characteristics of a soil are represented by a number called activity number. To get an idea about the swelling and the shrinkage characteristics of a soil, it is represented by a number called what, my dear students? It is represented by a number called activity number, that is N. So the swelling and shrinkage characteristics of a soil are represented by a number ratio called activity ratio. And here the activity ratio is defined as the ratio of plasticity index to the percentage of clay fraction. Now, my dear students, when I talk about the activity ratio, when activity ratio is less than 0.75, then it is low active. When it is less than 0.75, it is low active. When the activity ratio is between 0.75 to 1.25, it is medium active. When the activity ratio is more than 1.25, it is highly active. So why do you want to study about activity ratio? It gives you about the swelling and shrinkage characteristics of a soil. The swelling and shrinkage characteristics of a soil are represented by a number called activity number. So there is another question. For soils of specific origin, the activity number will be constant. If the soils are both are of, if we have different soils and they are having the specific origin, then the activity ratio will be constant. Okay, is it clear? Now see, remember my dear students, what is activity ratio? It is defined as the ratio of plasticity index to the percentage of clay fraction. The swelling and the shrinkage characteristics of a soil are represented by activity number n. And if the values are different for soils of specific origin, the activity ratio will be constant. If you see, these are the values of activity. Now I would like to tell you why Mont Morillette has the highest swelling and shrinkage. Imagine, sir, if the A value is more than 1.25 itself, it is highly active. When you think that activity ratio for Mont Morillette is almost greater than 4. So imagine that is the reason Mont Morillette has the highest swelling and shrinkage. I hope you are clear with the activity ratio. Now see students, I have a question for you. As particle size decreases, this is very important. As particle size decreases, what will happen to I am asking you students, as particle size decreases, what will happen to liquid limit, plastic limit or shrinkage limit? Sir, see, this is a very simple way to identify that. Now my dear students, if you see, as the particle size, suppose if the dia of the particle decreases, what will happen to the void ratio? Void ratio will increases. Now if you see the relation between void ratio and water content, A is equal to WC by G by SR. So here what is liquid limit, plastic limit? They are nothing but the water contents. So here E is directly proportional to water content. As void ratio increases, water content also increases. So my dear students, as the particle size decreases, what will happen to the void ratio? Void ratio will increase and water content will also increase. So you can write, as particle size decreases, liquid limit, plastic limit and shrinkage limit, everything will increase. Okay. Now see students, if you talk about the particle size, how the soil is going to vary. These are the things. Next, we have another parameter called sedimentation analysis. Okay, actually see students, I told you sedimentation analysis is useful for what? Sedimentation analysis is useful for what, my dear students? It is useful for classification of fine-grained soils. Sedimentation analysis is useful for classification of what? It is useful for the classification of fine-grained soils. Sedimentation analysis is useful for classification of which type of soils? If anyone asks me, it is useful for the fine-grained soils. Now see here students, remember sedimentation analysis is based on Stokes law. What, sir? Sedimentation analysis is based on which law? Stokes law. Here, okay, this sedimentation analysis is based on the Stokes law. Here Stokes law is valid for the particle size ranging from 0.2 micron to 0.2 mm. So there can be a question from one of you, sir, why it is applicable for the particle size ranges from 0.2 micron to 0.2 mm only. If the particle size is more than 0.2 mm, what will happen? Actually, if the particle size is more than 0.2 mm, my dear students, there will be a turbulent flow. That is the reason they told that sedimentation analysis is valid for Stokes law is valid for 0.2 mm. And if the particle size is less than 0.2 micron, what will happen is there will be a Brownian movement. So these are the true reasons. If the particle size is less than 0.2, you will observe a Brownian movement. And here if you see, if the particle size is more than 0.2 mm, you will observe a turbulent flow. You will observe a turbulent flow. That is the reason actually why, how this sedimentation analysis is, here the sedimentation analysis is based on Stokes law, and this Stokes law is valid for 0.2 micron to 0.2 mm. If the particle size is less than 0.2 micron, Brownian movement will happen, and if the particle size is 0.2 mm, more than 0.2 mm, turbulent flow. So here see students, settling velocity according to the Stokes law is given by the formula g by 18 into s minus 1 into d square upon mu. So this formula, whatever the settling velocity formula they have given from the Stokes law, can be simplified. Settling velocity, what is Vs? You can write it as settling velocity. My dear students, here the settling velocity is approximately taken as 902 mm. Here you can write it as 902 d square, 902 d square. See students, here the particle size d should be substituted in mm, and you will get the settling velocity in mm per second. This is very important, student. Suppose if the particle size in micron, you cannot substitute d in microns. You have to always substitute d in mm, and you will get the settling velocity value as mm per second. I hope you are clear with the settling velocity formula, that is g by 18 into s minus 1 into d square upon mu, where you will get settling velocity Vs is equal to what, sir? 902 d square, where d is the particle size, and the particle size should be substituted in what, sir? It should be substituted in mm, and you will receive the settling velocity in mm per second. Next, here we have different methods to determine the sedimentation analysis. First is the pipette method. So if you talk about the pipette method, I will tell you how the principle works. I'll go you the insight of the principle. Suppose, see students, you have a pipette, there might be a pipette which is a, so here if I observe, this is a pipette, okay, and if you have a beaker, there is a soil particles which are at here, okay, initially the soil particles are at a time t is equal to 0, they are here. After time t, the soil particles came to t1, and whatever the solution we have here is we call it as dispersion solution. Are you able to understand, students? There is a pipette inserted. Initially the soil particles are here. After a time t, the soil particles are here. So if you find out this distance, you will find out how much the soil has been settled. So settling velocity can be taken as what? Distance, how much the soil particles have settled, divided by the time t2 minus t1. If you take this as 0, it will be t1. Or if you take it as t1, suppose if you have taken this as t1 and if they have taken t2, it can be written as t2 minus t1. So here actually, see students, we are making one solution. This was a previous GATE question also. What is the solution used in pipette method is, we are using a solution called dispersion solution. In dispersion solution, what happens is, there can be 7 grams of sodium carbonate and so see here, it contains dispersion solution, and the dispersion solution contains 7 grams of sodium carbonate and 33 grams of sodium hexametaphosphate in 1 liter of solution. Okay, what do we have? This is dispersion solution, and this dispersion solution, how they have prepared is, it is a mixture of 7 grams of sodium carbonate and 33 grams of sodium hexametaphosphate in 1 liter of distilled water, because there should be some standard solution where the soil particle has to be settled. Based on that, we are going to calculate the settling velocity. And remember, my dear students, there is another method also called hydrometer method. And hydrometer method also, the principle will be same. In a hydrometer method, what you have studied in fluid mechanics or pipette method, these are also, the methods are same. But here in soil point of view, when I talk about the hydrometer method, the corrections are important. You remember, in hydrometer method, the meniscus correction is always positive and dispersion agent correction is always negative. And if the temperature during the measurement is more than the standard temperature, it will be positive, correction will be positive. If the if the temperature during measurement is less than the standard temperature, then the correction will be negative. So this is all about the index properties. So when I talk about the summary of this topic, index properties are useful for classifying and identifying the soil. What do you understand, student? Index properties are used to classify and identify the soil. And also we have studied about for course rank, we have studied about what, my dear students? We have studied about sieve analysis, and we also have studied about what, my dear students? Relative density in case of course rate. What the relative density is nothing but density index E max minus E minimum, E max minus E upon E max minus E minimum. So this will be useful for course rate. And when I talk about the fine grained students, we have discussed about what, sir? In fine grained, we have discussed about the terms called consistency limits, or we have discussed about the sedimentation analysis. And we have discussed about the indices. In consistency limits, we have discussed about liquid limit, plastic limit, shrinkage limit, and their important relations. And we have also discussed about the liquidity index, plasticity index, and all. Okay, so if I talk about the important formula in this chapter, so here I would like to write you the shrinkage limit formula, which is E by G, is very important, or there is another formula 1 by Gm minus 1 by G, and the another important formula you can write shrinkage ratio, that is equal to gamma D by gamma W, or it is the volume change in terms of dry volume to the corresponding change in water content. Sir, I am just giving the overview, that is the reason I might be fast. And we have different indices. IP is equal to what? WL minus WP, and we have IC is equal to WL minus W upon IP, and you know, remember that IC plus IL is equal to 1, and you also have to remember flow index, that is IF is equal to W1 minus W2 upon log N2 by N1. So we have different formulas here, my dear students. So these are the important formulas which you have to study in case of the consistency limits, or you in case of the sedimentation analysis, or in case of the index properties. And you also have to remember, I see we also have toughness index is equal to IP upon IF. So these formulas will be discussing some of the important problems in the next session. And if you are trying to attend the next session, students, it's my sincere advice to go through this video, because this video will help to solve the problems in the coming sessions very easily. Okay, so let us see. Now see, students, these are some of our toppers which we have secured in the GATE 23 exam, and we are proudly say that all our toppers have followed our stringent preparation strategy, and they have followed our concrete classroom subjects, and we have a concrete plan for the subject flow, how the subject has to be discussed in the offline coaching, and these are all the toppers list in the GATE 23. Apart from this, my dear students, in GATE, actually IMS GATE Academy is proudly giving you the GATE zero fee program, where it contains 100 plus hours of GATE coaching, where 100 means the complete 100 hours will be free for you. You just visit our website imsindia.com and visit the GATE zero fee program. It has 100 hours plus of coaching, and 12 chapter tests, 6 subject tests, and 6 practice tests. Apart from this, you can observe, see, what we provide at IMS GATE Academy is we provide 800 plus hours. And remember, students, offline coaching will always have a definite edge over the online coaching, and this has been proven practically also. The students who have taken the coaching in the offline have produced very good results, and we have centers at Bangalore and also at Vijayawada. So what we provide is 130 plus online tests, 20 to 30 theory books, 12 one-to-one mentorship, and revision classes, and many more. You can contact our advice at Bangalore. We have the contact numbers at Bangalore, Vijayawada, Ahmedabad, and other cities. Okay, and if you talk about the admissions at Vijayawada, this is our center. We have at Ben Circle, and we are the only institute in Vijayawada which is running the offline center. And Bangalore also, my dear students, if you want to understand for the concepts, we are also providing free demo offline coaching also. Try to attend this Saturday, Sunday also. We are giving the free demo lectures for all the branches. So if you are real Bangalore, if you are locating in Bangalore, feel free to come to IMS Jayanagar office and try to attend the free demo lectures. Thank you. I hope these sessions are helping you, and as I told you so many times, the complete sessions on the foundation course will be free, and we will be floating all the sessions daily at the same time. If you are really interested, please like and share, and thank you.